modulus principle. So please someone tell me the statement of minimum modulus principle. What is the statement of minimum modulus principle? Anshul? Anshul?
Yes, ma'am.
Please tell me the statement of minimum modulus principle.
Ma'am, if function is holomorphic in a domain and non-constant, then mod of f has no minima in domain.
No, it's not like that. It's like the minimum is attained at the boundary. No minima in the interior point of the domain.
Okay, ma'am.
Okay. So using that principle, we have to prove this theorem, the fundamental theorem of algebra. For that, if I assume that, let us assume that P is any non-constant polynomial and P of Z is non-zero for all complex numbers. We will prove this theorem via contradiction. And if I assume for any R positive, we are taking any arbitrary R and making the disk of radius R. Then we know that from the minimum modulus principle that this polynomial will attain its minima at the boundary. So there will be a some z naught belonging to C such that mod of pz naught will be the minimum. Such that minimum of mod of pz z belongs to D will be mod of pz naught. Using the minimum modulus principle. Is it clear? Is it clear?
Yes, ma'am.
Okay. Now my claim is that this P of Z naught is 0. So in contradiction, I can assume that if I take that P of Z naught is non-zero, then we can see that mod of Pz will be greater than mod of P, because mod of Pz naught is the minima for Z in the disk. So 1 by mod of Pz will be less than 1 by mod of Pz naught. If it is non-zero, then we can say that one of the maximum modulus will be the 1 by P mod Z naught is the maxima of 1 by mod Pz. In the disk. In this disk D. Is it fine? If minima is attained for P at Z naught, then maxima will be attained at Z naught for 1 by P. Is it fine? Also,
Yes.
for the polynomials, we know that mod of Pz naught will go to infinity as mod Z tends to infinity. Do you know the result?
Yes, ma'am. Yes.
Okay, which will imply that 1 by Pz naught will go to 0 as mod Z tends to infinity. From the limit definition, we can say there exists a R large, R positive, such that 1 by mod of pz is less than 1 by, we can choose epsilon accordingly. We are choosing epsilon 1 by p at 0 whenever mod z is equal to r. This will be true for every z whose modulus is equal to r. Now, this the previous r was arbitrary, which we have taken here. But now we are getting some r from the limit definition. Using this r in that disk, we have mod z is equal to r. So this will be true for mod z naught also. But this was the maxima. Therefore, we got a contradiction. Is it fine? Using the minimum modulus principle, we were assuming that mod of that pz was non-zero for all complex numbers, and we get at a contradiction using the minimum modulus principle. Is it fine? We can choose this as a epsilon. From the limit definition, we are getting this. Is it clear? Is it clear?
Ma'am. Ma'am.
Yes, yes.
Ma'am, is less than epsilon whenever mod z is equals to or
Because we know that this maxima and minima is always attained at the boundary. Therefore, we can take less than also, but we will take the equality.
okay.
Is it fine? Can we move to the next question?
Yes, ma'am.
Okay. Have you tried the next question? Next question is easy one. Let U be a bounded domain and f is some function from U closure to C. This f is a continuous function. In fact, analytic on this bounded domain U and also non-constant. These are all the assumptions of the function f. Now, what is our claim? That we have to show that maxima and minima is attained at maxima and minima of real part of f and imaginary part of f is attained at the boundary. Any ideas, class?
Ma'am,
Yes, Sita.
I'm letting that z equal to e to the power fz, then we will use maximum principle.
Yes, right. You're right. Because we know this fact that maximum of modulus e raised to power fz or minimum is equal to maximum of e raised to power real part of fz. You can verify it using that fz is plus iota v. You can verify this. And we now let that g of z is e raised to power f of z. Now, as this f is analytic on u, therefore g is also analytic because composition of two functions is again analytic. and this will also be non-constant in U. Now using the maximum modulus principle and minimum modulus principle, we will get that G will attain its maxima and minima at the boundary. And from there, we also know that this exponential is a increasing function. From there, we can say that maxima and minima of the real part of fx is also attained at, this is for the real part of x, will be attained at the boundary. Is it fine? Is it fine? And for the imaginary part, what is the idea? We have to,
Z equal to e to the power minus iota f it.
yes, right. E raised to power. Now we can choose e raised to power minus f z. For there, that this same argument will work for the imaginary part of f. Is it fine for others? Arpit?
Yes, ma'am.
Okay. Sarthak?
Yes, ma'am.
Okay. Next question. Now given that f is an entire function, what is the definition of entire function? I hope
Whole of
everybody.
the second whole of C.
Yes. Now we have to show that there exists a C complex number with its modulus equal to 1 such that f of z is equals to c z raised to power n for all z belonging to C. We have to show that the function is this type. So any ideas? Have you tried this question? I know this is a bit difficult. So first of all, we can assume that this function f does not have infinitely many zeros in the disk, open disk. If it will have infinitely many zeros in unit disk, then what will happen?
By identity theorem, it will reduce to zero function.
Okay, it will be the zero function, and then this thing will not be true. Is it fine? Now we are assuming some other function, capital F. Yes, first of all, we have finitely many zeros of this function in the unit disk. Let these zeros be AIs with the zeros of that is. Using these zeros, we are constructing a function capital F, which is written, which can be this. Assuming finitely many means n zeros, z minus ai upon n minus ai power c. So you have to verify some things about this function f. First of all, this F is analytic in the disk. Can you people see this?
Yes, ma'am.
We know that this FZ is analytic and the problem can be created using these AIs. But these AIs are already the zeros of FZ. So these will cancel out in a way. So we will left with no similarities. Is it fine?
Yes, ma'am.
Also, this FZ will be non-zero in this disk because uski all the zeros will cancel out and FZ will not have any other zero.
Yes, ma'am.
Now the third thing to observe is that modulus of Fz is equal to 1 for mod z equal to 1. Please calculate it. You can easily see this. Once you get this, you can easily see that the modulus of capital Fz will be also equal to 1 for mod z equal to 1. Can you realize this result when mod z is equal to 1? These two things are equal. How will you show that? This is a simple calculation. You have to see this. You can verify this. From there, you can observe that mod of capital Fz will be equal to 1 for mod z equal to 1. Is it fine? Now we have seen that this capital Fz is non-zero in the disk. So we can apply because capital F is also analytic, then 1 by F will also be analytic. So apply maximum modulus principle on F and 1 by F. So what can we conclude using this? Yes, Sanju. What can be the conclusion? You can realize that we can apply maximum modulus principle on both F and 1 by F. Is it fine? Sarthak,
Yes, ma'am.
so what can be the conclusion from this? If we apply maximum modulus principle on both capital F and 1 by F, what can be the conclusion? What is the statement of maximum modulus principle? Arpit?
Yes, ma'am.
What is the statement of maximum modulus principle?
If f is a holomorphic function on a domain, then it attains its maximum on the boundary.
Okay. If capital F and 1 by capital F both will attain its maxima on the boundary, then you can say that let Z belongs to the disk. If mod Z is less than 1, then 1 by let maxima is attained, maxima of F is attained at boundary and the modulus is 1 for the boundary. For any interior function, it should be less than 1. 1 by F should be also less than 1 and F should be also be less than 1, which will imply that modulus of Fz is always 1 on the disk, which implies F is a constant function. Is it okay? Therefore, we can write Fz as let the constant be C. Now, what is the conclusion we know about, what is the hypothesis which we know about F? F is entire, so it cannot have any singularity. And these are the singularities, which will imply that these AI should be 0 for all I. Can we conclude this?
Ma'am,
Yes,
mod
we
f
can.
z is equal to 1. How?
See, देखो F का मॉड भी 1 होगा इंटीरियर में और 1 by F का मॉड भी 1 होगा इंटीरियर पॉइंट पे किसी भी 1 से छोटा मींस 1 से छोटा होगा बिकॉज मैक्सिमा जो है अटेन हो रहा है बाउंड्री पे और बाउंड्री पे मॉडुलस 1 है 1 का भी और 1 by F का भी.
Now it is strict inequality, then how we conclude then this equal to
Okay,
1?
sorry. This is not strict inequality. This is less than equal to. इंटीरियर मैक्सिमम मॉडुलस प्रिंसिपल अगर हम f और 1 by f दोनों पे लगाएंगे तो हमें वहां से कंक्लूजन मिलेगा कि फंक्शन ही कांस्टेंट फंक्शन है क्योंकि f का मैक्सिमम मॉडुलस भी 1 है और 1 by f का मैक्सिमम मॉडुलस भी 1 है. ये पॉसिबल तभी होगा जब फंक्शन का ही मॉडुलस 1 हो. मेक सेंस?
Yes, ma'am.
Okay. Now this small f is entire and we have these singularities ai's bar in this function. So these singularities should be 0. Means this ai should be 0. Is it okay? We cannot have singularities here, right? So from there we can have fz equal to c raised to power c z raised to power n, which will imply that also mod of fz is equal to mod of z. This is mod z, mod of z. If mod z is equal to 1, then mod of fz is equals to 1, which implies that mod of c is equal to 1. That's good. Easy calculation? Is it an?
मैम
Is there any difficulty? Yes.
एक बार स्टार्टिंग से रिपीट कर दो.
Okay. See, first of all, we are assuming no. First of all, we can see that this function will not have infinitely many zeros in the unit disk. Because if it will happen, then the function will be identically zero from the identity theorem. Okay?
Okay, मैम.
Okay. So in the disk, we are having only finitely many zeros of this function f. So taking these zeros as ai's from 1 to n. Using these zeros, we are defining some other function, capital F z, in this way. Small f z upon product of these functions. Now we have to observe some facts about this function capital F. First of all, this function is analytic in the unit disk. Second, this is non-zero in the open disk. Third, we can assume that we can see that its modulus is also 1 when mod z is equal to 1. These are the three observations we are making about this capital F function. Is it okay? Now we know that this is non-zero. Therefore, we can talk about 1 by f also. F is analytic, 1 by f is non-zero. Therefore, both of these are analytic in the disk. So,
मैम
yes,
थर्ड वाला पॉइंट एक बार दोबारा बता सकते हैं.
कौन सा point?
थर्ड mod f z equal to.
Okay. For the third point, we have to calculate the modulus of capital F z, and we know that the modulus of small f z is equal to 1 when mod z is 1. So the question remains for this thing. What is the modulus of this? Now I am saying that modulus of z minus ai is equal to modulus of 1 minus ai bar z. You can prove this. Try to calculate it. I have written that you have to verify this.
Okay, मैम.
You can verify it like z bar minus ai z bar minus ai bar z plus ai bar. This is one. Same is here. 1 minus ai z bar z ai z z bar plus ai bar z bar. Now z bar is 1. These two things will be equal. From there we can get that modulus of f z is equal to 1 when mod z is equal to 1. Is it okay?
Yes, ma'am. Okay.
Next, now we can apply maximum modulus principle on capital F and 1 by capital F. From there we can say that this function, we can conclude that this function is constant on the unit disk, and if capital F is constant, we will get that we can assume that constant to be C, and from there we can get that small f z will be this function. Now this function is entire, so it should not have any singularity. From there we can conclude that these ai should be 0. If these ai's will be 0, then the function will remain this. Now the thing which we need to show is the modulus of c is 1, which is easy to see. Is it okay?
Yes, ma'am. Okay, clear now.
Okay. Okay, the fourth question we will discuss it in the next tute. We can move to fifth question. So determine the singular points and type of singularities of the following functions. The fifth question is we have to determine what is the singular point? But what do you know about the singular points? The topic singularities has been covered in the class, right?
Yes, ma'am.
Yes.
So what is the definition of singularity?
F is holomorphic in the neighborhood of that point, but not holomorphic at that point.
Okay. So what is the difference between isolated singularity and non-isolated singularity?
Isolated singularities have a limit, does not have a limit point.
And non-isolated singularity? Okay, read the definition of isolated, non-isolated, removable, pole, essential, non-essential. All these singularities, concept of singularity should be clear to you because it has been explained in the class. So for the we will first of all the given function is 1 upon x square plus x raised to power 4. So what are the singularities of this function?
Zero and plus minus iota.
Okay, where the denominator will be 0. This implies this, or z square plus 1 is 0. That is z is plus minus iota. We have three singularities and we have to find out the nature of these singularities. For z equal to 0, you can see that, let me call this function as f set. What is the limit of this? Is it infinity?
Yes, ma'am.
So what can be the nature of this uh, uh, point f z is equal to 0?
Pole.
Polar
Z is equal to 0 is the polar. Now we have to calculate the order of the pole. First calculate this limit. This will be
infinity.
this,
1.
which is non-zero, and this will be for all n greater than equal, greater than 2.
0.
From there, but we can conclude the order of
2.
2.
order of this pole will be 0, will be 2 at z is equal to 0. Similarly, you can see that for z equal to iota, this limit is going to infinity, and z minus iota fz limit is what is this limit? Please calculate these two limits. This is easy one, right?
Yes, ma'am.
Okay,
And
calculate
last is
it.
0 and last second is minus 1 upon 2 iota.
Minus 1 upon 2 iota, which is non-zero. So what is the order of pole at Z?
One.
When the order of the pole is 1, we also say it to be the simple pole. Next thing is we have to write the Lorentz series of this function around this 0 iota or minus iota. So how can we write the Lorentz series? So what is the Lorentz series of function? This is this given function, right? We can also write it as 1 plus z square minus 1. Yes or no?
Yes. Yes.
Also, we can open binomial here.
Yes, ma'am.
So we will get a series. So what is the definition of Lorentz series? Nobody has told me. Yes, Sita.
If fz has isolated singularities only, then we can write it in Lorentz series forms as that summation n belonging to z fz z minus alpha to the power n, where alpha is any isolated singularity.
Right. So, and what is the definition of a residue? So this will be the Lorentz series of this function, right? Around 0. Because we have written it in the form of summation an z minus 0 raised to the power n, where n belongs to the integers.
Minus 1.
First of all, please tell me the definition of residue.
And coefficient of 1 upon z.
So what is the coefficient of 1 by z here?
0.
0. Not minus 1, it's 0. Now, next thing is we have to calculate the Lorentz series around iota and minus iota also. So how can we do that? This is the function, right? We can write it as minus iota plus iota whole square, then minus iota as it is, then minus iota plus 2 iota. Now we can write it as z minus iota as it is. We can take iota common. It will be. We can take 2 iota common here. So this will be iota, 2 iota will be 1 by minus 1 by 2, z minus iota as it is, and 1 plus z plus iota by 2 to the power minus 2, and 1 plus z plus iota, z minus iota. You can calculate this. You can do these calculations, right? So what was the trick? We are introducing, because we need the power this series in terms of z minus iota. We have to write it like this. So the trick is we are introducing iota and iota in both the terms and then applying binomial. Is it okay? Now you can do this calculations, right? Yes or no?
Yes, ma'am.
Okay, after this calculation, you can find the residue also. Okay. Next time, please, you people tell me what is the residue of this function around z is equal to iota and minus iota both. And this question number 5, try to complete it. Try to write the singularities for all the parts. Any difficulties you can tell me. You can ask in the next tute. Try to finish this 5th question. You can do this, right?
Yes, ma'am.
All the parts will not be discussed in the tute. Only the difficulties will be discussed. Try to write the Lorentz series. Try to find out the residues. Okay. Any difficulty for today's tute? Anything which you haven't understood? Is it fine for everyone? Can we conclude this session?
Yes, ma'am.
Okay, this notes will be shared on the Teams itself. If you have any difficulty, you can email it to me. I am writing the email ID here.
Okay, ma'am.
You can note it down. Okay. You can note this email ID. Then I'll include. Okay. Thank you all.
Thank you, ma'am.
Thank you.